Morning, everybody. This is Morgan. So we are talking about buffers in AP Chem today. Now, a buffer can be defined a few different ways. Typically, in a textbook, you're going to see a solution that resists changes in pH when small amounts of acid or base are added. Now, that's a very good definition, except that it doesn't actually tell us what the buffer's made of. It tells us what it does, and that's good. This is typical of a biology book to talk about it this way. Now, a chemist would probably say something like a weak acid and its conjugate base. So when you mix a weak acid and its conjugate base, you get a buffer. So HA can be our weak acid and A minus would be its conjugate base. So if I have a mixture of this and I add OH minus, the OH minus reacts with the HA, and that gives me H2O and A minus. I already had A minus there. If I add H3O plus, an acid, it reacts with A minus, and it produces H2O and HA, which was already there. So I'm just adjusting the amounts of the HA and the A minus. I'm not really changing the composition of the solution, so that's how it resists those changes in pH. Now, identifying a buffer is an important thing, being able to look at a mixture and seeing if it is a buffer or not. So we'll do several of those. First off, I have 50 milliliters of 0.1 molar HCl. HCl is a strong acid. And 50.0 milliliters of 0.1 molar NaOH. Now let's always remember molarity equals moles over volume. So moles equals molarity times volume. And in both these cases, I have the exact same number of moles of strong acid, strong. This just neutralizes. No buffer. That is not a buffer. No, no, and no. So now I have 50 milliliters of 0.1 molar acetic acid, which is a weak acid, and 50.0 milliliters of NaC2H3O2, sodium acetate. Now that is the conjugate of the weak acid. Took the hydrogen off, just threw a sodium on to keep the charge balance. Okay, yeah, that's a buffer. That's exactly what a buffer is supposed to be. In fact, we have the exact same concentration and volume of each. That's good for a buffer. We like that. Now, in letter C here, we have HF mixed with NaF. So yes, it's a buffer. Same volume and molarity. Yeah, that's all cool. That's what we want. Now, let's make it a little more complicated. And this is actually how we prepare buffers. So we need to talk about that a bit. We have 50 milliliters of 0.1 molar acetic acid, but we also have 50 milliliters of 0.1 molar sodium hydroxide. Now, they will react with each other via HA reacts with OH minus to give H2O and A minus. So I have, let's just do it this way, HA plus OH minus to give A minus in water. We're going to do a little mini ice type table. 50 milliliters times 0.1 molar is 5.0 millimoles. And 50 milliliters times 0.1 molar is 5.0 millimoles. So they react with each other. Perfect stoichiometric mix. So when I'm done, I don't have any HA, I don't have any OH minus, and I've gained some A minus. So no, this is not a buffer. I have the A minus, but I don't have the HA. Now let's look at the same thing in E, except with differing amounts. HA plus the OH minus to give me A minus and H2O. So 50 milliliters times 0.1 molar, that's 5.0 millimoles. 25 milliliters times 1.0 molar is 2.5 millimoles. So minus 2.5 minus 2.5, because it's the limiting reactant, 0, 2.5, 0 plus 2.5, I've got 2.5. So I have HA and I have A minus present. Yes, that's a buffer. Okay, I have to have both of those present. So the way we actually make a buffer in the lab is we take acetic acid and we do add NaOH to it. Okay, that produces the A minus. That's how we produce sodium acetate to begin with. So, in this case, 50 milliliters of 0.2 molar acetic acid. Okay, same reaction again. So 50 times 50, that's 10 millimoles. 50 times 0.1, that's 5.0. So minus 5.0, minus 5.0. I'm choosing the smaller one, the limiting reactant. 5.0, 0, 0 plus 5.0, 5.0. Yep, I've got HA, I've got OH minus. This is a buffer. Now, we've done 3 in a row involving acetic acid, and I don't want you to think that it's the only thing we use for a buffer. What if I have F minus? I react it with H3O plus from a strong acid. It produces HF and H2O. 50 milliliters times 0.1 molar is 5.0 millimoles. For the H3O plus, I have 2.5 millimoles. Minus 2.5, minus 2.5, that's going to be 0. 2.5 there. 0 plus 2.5, 2.5. There, I've got HA, I've got A minus. Yes, that is also a buffer. Okay? Alrighty, so at this point, let's flip on over to the next page. I want to develop an equation for you here. You would not be expected to develop this equation on your own, and in fact, you don't have to ever use this equation, but it's incredibly convenient. Okay? So, when we are dealing with a weak acid, we find the H plus concentration using the equilibrium constant and an icebox. That's Ka. Now, if I want to isolate the H3O plus to calculate the pH, that's going to equal Ka times HA divided by A minus. Yep, got that correct. Now, to find the pH, I need to take the negative log of the H3O plus. Okay, so the negative log of the H3O plus equals the negative log. Now remember, log of AB equals log of A plus log of B. So I have the minus log of the Ka plus the minus log of HA over A minus. Okay, minus log of the H3O plus is the pH. Now, it's actually the same thing here. When I do the negative log of the Ka, we just call it the pKa. Negative log means P. Minus the log of the ratio of HA divided by A minus. And this is a very convenient thing called the Henderson-Hasselbalch equation. Okay? Now, let's do the same problem 2 different ways. Okay? We have an equilibrium of 0.1 molar ammonia and 0.1 molar ammonium ion. That is a buffer. So, classic icebox method, which you can always use. Many of you will. So we're going to have a KB this time. And that was given the value of KB. It equals 1.6 times 10 to the negative fifth. Okay. Now, when I make my icebox, little twist to it. 0.10 molar, ignore, and I do have an original concentration of 0.10 molar for ammonium. Minus X, 0.10 minus X, plus X, 0.10 plus X, and I don't know why I said that. Water. Sorry about that. 0 plus X and X. So over here, what I end up with is 0.10 plus X times X over 0.10 minus X equals 1.6 times 10 to the negative fifth. Now, K is small enough that I can do approximations. Otherwise, I get a pretty ugly quadratic here. So the minus X is gone. And how about we take away the plus X? Same concept, right? And now I have 0.1 divided by 0.1, so they cancel. So basically, X, which equals hydroxide, equals 1.6 times 10 to the negative fifth. So my POH equals 4.8. So my pH equals 9.2. It's called 2 sig figs there, so 4.80, 9.20. There you go. Now, you can do that on all the tests. Everything will be great. We do have a shortcut method here. pH equals. Now, I need the pKa. Well, I know that the negative log of Ka is the pKa. I've got the Kb. All right, so why not just find the negative log of Kb, which will equal the pKb, pKb, and we'll subtract that from 14. So the negative log of 1.6 times 10 to the negative fifth is 4.80. That's the pKb. So the pKa equals 9.20. So pH equals 9.20 minus the log of. Now, HA is ammonium because it's got one more hydrogen. That's 0.10. The other one is also 0.10. So even if I flip those, I get the same answer. 0.1 divided by 0.1 is 1, and the log of 1 is 0, so the pH equals 9.20. It's a little slicker way of doing it, okay? I kind of like that approach. Just me, you know. So, this buffer has a pH of 9.20. But the pH of just regular old 0.1 molar ammonia would be 11.1, much, much higher. So why is this pH lower? If you look in this reaction, by having the ammonium already present, it shifts the equilibrium drastically back to the left, which means it's decreasing the amount of hydroxide ion that's present. Okay? All right, so let's call it Le Chatelier. That's the explanation. So I've got a few questions here that I basically just designed to see, can you distinguish between which species is HA and which species is A minus? So here, pH equals, I need the pKa. So the negative log of 2.9 times 6, that comes out to be 7.54. Minus the log of. Now, HClO will be the one with the hydrogen. That's the HA, it goes on top. 0.050. KClO, that will be the one without the hydrogen, that goes on the bottom. 0.100. This ends up equaling 7.84. 85, somewhere right in there. Okay. Do it for HF, pH. equals the negative log of the Ka is 3.13 minus the log of, okay, HF is 0.1, A minus, which is the F minus, is 0.2, and that ends up equaling 3.43. Sorry, a little dyslexic moment, 3.43. Okay, so can you tell the difference between HA and A minus? HA, A minus, HA, A minus. Did I mention you need to know your polyatomic compounds? All right, so one more page here, dealing with buffers. We'll do one last question like that, just because I want to establish a buffer that we're going to really answer several questions about. pH equals, now the pKa is 4.76 minus the log, and both of these are 0.10 molar, so that equals 4.76. So there's the acetic acid sodium acetate buffer we're going to deal with. Now, what is the pH after adding 0.001 moles of NaOH to 1 liter of this buffer? So, OH minus is going to react with HA from water and A minus. So, 0.001, we can call it an icebox if you want. So 1 liter times 0.1 molar, so this is 0.100 and 0.100. Minus 0.001 gives me 0. Minus 0.001 gives me 0.099. And plus 0.001 gives me 0.101. Now those are moles. Okay? That's fine, because it's per 1 liter, which means it's also molarity. Or I can just think of it as, since it's a ratio here, the volumes cancel out. So minus the log of, now the HA is 0.099. The A minus is 0.101, and this equals 4.77. Now that's hardly any change whatsoever, 0.01 on a logarithmic scale, okay? If I had dropped that much base into some pH 7 water, it would shoot up to a pH of about 11, which is, 4 full pH points. And this is 1/100th of the pH point. Okay? Buffers do a good job. They really do. Okay? Now, this I'm going to add HCl to it. So the H3O plus will react with the A minus. It'll produce HA in water. Do the icebox. 0.001, 0.100, 0.100, minus 0.001, minus 0.001, plus 0.001, and that gives me none of that, 0.099, and 0.101 there. So this time the pH is going to equal 4.76, the pKa, minus the log, and I have 0.101 over 0.099, and this equals 4.75. So I add a considerable amount of acid. The pH only drops 0.01. Here I added a considerable amount of base, and it only goes up by 0.01. All right, buffers work. Okay, now, here, I'm dealing with factors of 10 in this question. 1 molar sodium acetate, 0.1 molar acetic acid. pH equals 4.76 minus the log of 0.10 over 1.00. That equals 5.76. But in this next question, I reverse it. Okay? This time, it's minus log of 1.00 over 0.100, and that equals 3.76. Okay? So, Why number 7 more basic? It's more basic because I have a greater concentration of acetic acid. Okay? Or, no, sorry, said that backwards. Forgive me. It's more basic because I have a greater concentration of sodium acetate. Why is this one more acidic? Because I have a greater concentration of the acetic acid. Okay? We do a lot of things with factors of 10. Makes for easy logarithms. Okay, now, what if I diluted this buffer? Instead of having the total volume of 200 milliliters, I just pour in distilled water to make 400 milliliters. The pH doesn't change. It's still 3.76 because the ratios stay the same. These ratios stay the same, which means the pH stays the same. Okay, now this is an interesting question that was meant to lead you into a lab that we were going to do in class. Okay, so we have 8.2 grams of NaC2H3O2. I'm going to change that into moles. 1 mole. The molar mass is 82.04. And that equals 0.100 moles. Now here, 17 milliliters is 6 molar, so 6.0 moles per liter times 0.017 liters. That equals 0.102 moles. Okay, this is A minus, this is HA. They're basically the same number, okay, when you round off. Okay, so pH equals 4.76 minus the log. Now you're going to wonder why I don't divide them by the volume. I don't have to. Because if I did, just show you what happens. Divide by 100 milliliters. Divide by 100 milliliters. Now what happens to these volumes? They cancel out. So it's still the same ratio. Now that equals 4.76. And the reason this question is here is I then have you get up and go and measure out 8.2 grams of sodium acetate and 17 milliliters of EDC and make the buffer. Then I have you split it into a few different beakers, and we literally drop in that much NaOH, and we drop in that much HCl, and we measure the pH changes, okay, just to see how that happens. Okay, there you go. That's a little bit about buffers. This is Morgan, signing off.